Now, the piston is attached to one shaft. You can see that this is the shaft which goes internal to up to this. It is there. Okay, the fixation. Now, if you apply a force to piston, piston can move inside the cylinder. Please note that there are two chambers. One is chamber A, chamber B. Between the piston, correct? Left side of the one chamber B, I can say the A and B. These chambers are filled with fluids. Fluid can be gas or it can be liquid. Okay. So now both the chamber completely filled with this one. There is no gap. And many times we use liquid. Sometimes we use it as air also. That is called air damper. Nowadays, in the new vehicle, correct? If you see Volvo bus, all those things, they say air damper. Air damper can suppress even minute variation road fluctuation. That is what the job of the air damper. But they can, the force generated by damping force is very limited. That's why they use both. Correct? Most of dampers, suspension system using damper, all automobiles are using. Those damper use liquid damper. That means the cylinder is filled with a liquid, and inside the liquid a piston is moving. That's what is shown here. You can see that. Now, if you apply a force, the piston can move from the center position left or right. It can move from center position, move left or right. Now, main thing what you have to notice, the size of the piston is slightly smaller than the inner diameter of the cylinder. This is the cylinder. Correct. Here for understanding, but they shown as glass. Many times it is made of metal. Correct. Glass will break easily. So this is the cylinder, and this is the piston. Correct. You can see there's a small gap. Now, when pistons start moving from left to right, the fluid in chamber A, if the piston is moving towards, the force is applied like this, in this direction, right to left, the piston will move from the center position towards there. Now we have filled the chamber with a fluid. Fluid is incompressible. That means the fluid in the chamber A should come to B, then only piston can move. That means only where the fluid can go is this small gap. You can see that there are small periphery of this one. It is circular in shape. This gap from chamber A to chamber B, the fluid is going. Rate at which fluid is going, velocity of fluid is going to create opposition force. Correct? Fluid has some viscosity, the gap size, area of the gap size, all these things will decide how much fluid can move from left to right, when the piston is moving right to left through the gap between the piston cylinder. So that depends upon proportional viscosity, correct, and the gap area of this gap, because it's in cylinder. So if these two are fixed, then amount of the damping force, that what we'll call a damping force, FD. FD is proportional to C into, sorry, here we forgot, C into D by dt of X. This is called linear force, correct? There are two types of damper. If the piston is moving left and right, that is called as linear damper. Instead of that, you can see that another type of damper also available, which is called rotary type damper, in which again you have a cylinder, inside which you have a vane-like structure, correct? This is the vane. Okay, and you can see the shaft is coming out. If I apply a torque to this one, this is the body of the damper. That is nothing but cylinder. It is filled with viscous fluid. Entire this one, you can see the blue color is the viscous fluid, is filled with that, and the damper is going to not move left and right, it is going to rotate. If I rotate this shaft, damper will rotate. You can see that there's a small gap between the damping, that is which you call a vane, or it is basically a vane having some thickness. In this gap, fluid is going to, because this is chamber A, this is chamber B, fluid has to go when it rotates. That means it can go through only this chamber. The gap and the viscosity of the fluid is going to decide the opposing force of the rotary motion. That we call the torque. The rotary type damper, torque is generates Opposing force is a torque which opposes the motion. If, for example, the vane is moved from clockwise direction, rotates this one, FTD, a damping force act in opposite direction. Basically, trying to stop the motion, correct? So amount of force can be calculated using this formula. So here you say d by dt of theta. How much the theta is varying, correct? The vane rotation. Okay. In this case, the displacement d by dt of x. X is the displacement of the piston with respect to central position. That is proportional to what you call as C. C here is called damping constant. Note down. It is called as damping constant. Whether it is a rotary damper, all those things, it provides a opposing force that is proportional to what you call a damping constant, and that is proportional to velocity. Correct. So I can say V1 minus V2. Correct. D by dt of x1 minus d by dt of x2. Originally, it was in some position. From position that is I call x1. From that, it moved to new position x2. When it moves, d by dt of that is nothing but velocity. Correct. Initial velocity might have this is final velocity. Correct. You can say that this initial velocity, final velocity, and based on that, you will get a value that multiplied by the damping constant is force developed. In case linear damper, in case of rotary damper, it is a opposing torque it is produced. That proportional d rate of that is angular velocity. I can say theta is displacement. This is velocity. D by dt of theta is nothing but velocity. Multiply damping constant. The damping constant depends upon the fluid viscosity and the area gap between the vane and the cylinder. This is what how it works. Now I told you the damper absorbs energy and dissipates. Correct. Amount of the power consumed by damper is proportional to P equal to F into d by dt of x, which can be written as C into d by dt of x square whole square. Correct. This is nothing but C into v square, velocity square, where C is called damping constant. Power P equal to damping constant, damper multiplied by velocity. Correct. In case of linear, in case of angular, omega square, because C into V whole square is the power dissipated. Now, power is instantaneous amount of the energy dissipated. But if you want to find the energy, you integrate the power over the time. Integral P dt. P is the power. Dt, you are going to integrate 0 to T. P dt is this one, which can be written already. We know the P equal to C into d by dt of x square. That's what you know. If you integrate, finally, you will get this equation. E will be equal to C into d by x dx or integral F into dx. This is the amount of energy dissipated by the damper can be calculated. Okay. So I told you now there are two types of damper. I want to give little more. Correct. Here you can see that this is my cylinder, a cylindrical, this one completely enclosed, filled with viscous fluid, light blue color viscous fluid. Then I have a piston which is attached to a shaft. This is the piston, correct? Having is which is going to move inside the cylinder which is filled with a viscous fluid. The piston is attached to that. If I apply a force, correct? I apply a force and then the piston from the center position can move left or right. Anyway, it can move. 0 is the center position, it can move. Depending on the type of whether you are applying compressive force or this one, tensile force. You can pull the piston left or right. When you do that, the amount of the damping constant, please note down this equation, correct? So damping constant provided by linear damper. Because the moment is linear, it is a piston type damper. The piston is moving inside a viscous fluid which is filled inside this one. Fluid cannot escape anywhere. I say this is chamber A, this is chamber B. If piston is moving from right to left from the central position, what will happen? Fluid from the A chamber will move to B chamber through this gap in surrounding. So the gap is given as H, correct? And then other dimension given. So now the damping constant or damper. This is the final equation for this kind of damper. Different type of dampers are there. For this type of damper, we can say the damping constant or damper, which is nothing but opposing force. When this is the applied force, the damper force opposing force. That is proportional to damping constant and velocity. Velocity is what depending on the force supply, correct? So in that case, 6 into pi into mu into L divided by H cube multiplied by R2 into H by 2 whole square minus R1 square, whole thing multiplied by again R2 square minus R1 square divided by R2 in R2 minus H by 2 minus H. All the parameters explained. This gap is gap between the piston top surface and cylinder inner. That is what the gap size. That is given as H. R1 is already made diameter of the radius of the sap. Correct. This is the sap on which piston is attached. So radius of the piston, the shaft is given R1. Correct. From the center axis to piston inner, this one is given R2. The gap between the piston and the cylinder, that is H, that is given a H. And 6 is constant, pi is constant, mu is called as the fluid viscosity. What is the viscosity of the fluid? That is mu. L is the width of this width. This width is called as L. Correct? Width of the piston. So once you know that, you can find out what is damping constant. But if you buy a damper, correct, most of the time C value will be given by the manufacturer. Correct? C value will be given by manufacturer. If you are designing your own this one, you can use this formula. If you are going to use this kind of piston type with the orifice and the between the cylinder inner wall and the piston, this one. Okay. Now that we looked into this one, dampers, correct? Now this is the equation damping this one depending upon type of this one. Already we talked about it. We already studied. There's no need to see this once again. Here it is there. I think this slide is a repetition. Okay, this is not needed. Anyhow, now that you know that this is, if it is a linear damper, force generated equal to C into velocity. This is not C into V. V is the velocity of the piston. That depends upon the, already we saw the equation, all those things. This is called damping constant, correct? Damping or damper, that can be written like this. Already we saw this. Now, how they generally represented the damper in the documents, correct? Damper is represented something like this. This is symbol for damper, correct? So this represents cylinder, this represents piston, correct? This is symbol for damper. Okay. Now, if I wanted to write the mathematical model or transfer function, mathematical model of damper from this equation, we are going to write from this equation, mathematical model. We know that when you write the mathematical model, we call it a transfer function model. G of S equal to X of S divided by F of S, where F of S is given as input to the damper and the piston position is called X of S. Correct? Piston, please note the cylinder is fixed. The piston only moving inside the cylinder filled with this one. So the position of the piston is called X of S. That is the output of the damper, is nothing but 1 over C into S, where C is damping constant of damper. S is called Laplace variable. It is called as Laplace. This is called transfer function of the damper. This is called mathematical model or transfer function of the damper. Okay. Next, we are going to see mass element. Correct? Any physical object which is in solid in shape will have mass. Correct? It can be any material, plastic, rubber, steel, metal, anything, ceramic, anything. It has a mass which is in a solid in shape. It has a mass. Okay. Now, when we talk about mass element, as per Newton's law, the behavior of mass element, generally we consider point mass. because generally mass has a volume, correct? And the amount of matter in the given volume is called as mass. And for whenever you want to consider some model development, we say that it's a point mass. That means the entire mass. I say that this is mass of the Earth, correct? Mass of the Earth 10 into 23 kg, something like that. I don't know exact number. So this represents mass, and I say that it is. I have a sun. Sun is shown like this. Is massive 10 power 29 kg, something like this one. When we talk about the between these two is the gravitational force, right? There's a gravitational force. Gravitational force. In that case, I'm showing this because Earth size we know so big, but I say that this is a point. It is called point mass. I call this as point mass. Earth is represented as a point mass, as a small dot. Similarly, sun also shown as small dot. Right? I can say small dot, something like this. This is the Earth. This is the sun. But it is represented with whole mass of this one. That's what called point mass. Instead of showing actual size, I cannot show. Correct? Instead of we say point mass, consider like this for all the calculation. When I do that, okay, point mass is this one. We know that the forces, summation of forces acting on a mass element, okay, is called F equal to mass element mass, which general unit is nothing but kg. Correct? Kg is the unit for mass multiplied by acceleration. So this is called FMA, F equal to ma, where m is the mass of the object, a is the acceleration, F is the forces acting on it. Correct? So, for example, they say summation of forces. Why we are saying is, for example, I have a mass. Correct? I have say 1 kg. 1 kg is mass. I'm applying a force like this from left side. Correct? I say that it is a 10 Newton force. And I am giving another force from right side. I say F1 of t. This is F2 of t. Right? So I am applying, this is 5 Newton force. The net force acting on this F of t on the 1 kg mass is nothing but F1 of t minus F2 of t. Correct? So that means this is nothing but summation. That's why. So some force is acting from left, another force is acting like this, another force is acting something like this. The total force is acting on the object. This one object is nothing but summation of all the forces acting should be equal to mass into acceleration. For example, we take only two forces, right? If I talk about two forces, we talked about two forces, left and right, which is acting. Now, this is 5 Newton. The net force is acting toward this. Summation is nothing but 10 minus 5 is the 5 Newton. That means the resultant force, I can say F equal to 5 Newton only, because this one force is pushing this side, other person push side. The net force is if we add both, one is plus, other one minus, plus 10 minus 5, then we will get plus 5. That is the resultant force is acting on it. Correct? This is force applying. This should be equal to mass into acceleration of the object. Because of force, the object is accelerating from left to right in the movie. Correct? That acceleration multiplied by mass of the object should be equal to the resultant force. That's what Newton's law is saying. Okay, we have seen this. Then, as per Newton's law, the behavior of a mass element, for example, point mass, correct, of which, for example, the force can be linear force, correct? A force is acting F of t, which is a mass, because of there's a displacement x of t, because of there's an acceleration a of t. Force is applied. This is a mass element, displacement happening, and if you do that, there's a velocity v of t. Then again, you have acceleration. This is x of t. The d of this is nothing but d by dt of x of t. Displacement differential, get this one. D by dt of velocity is nothing but acceleration. That's what we are talking. This is for linear forces. Instead of that, I have a mass, correct? Yeah, for example, like a disc having a mass m, which is attached to an axis, correct? A shaft is there. Now you apply, if you try to rotate this mass, instead of linear motion, if you do rotary motion, as per this one, Newton's law, we know the behavior mass element, thinking that because you know that this has some radius, all these things, this also considered as a small point mass and it is rotating, right? In that case, yes, area is very small, and from center axis, this is center axis, it is rotating. Entire mass is, for example, this is 10 kg, that is represented by a point mass. When you say the point mass is this one, this is 10 kg, and if you give a torque to rotate it, you need, instead of linear force, you give a torque, rotational force. Then the rotational force is nothing but I into omega, where I is called as moment of inertia, angular acceleration is given as omega. Here, correct? So, sorry, this should be extremely sorry, it should be alpha, I alpha. Omega is angular velocity, alpha is angular acceleration. So, similar to F equal to ma, mass into this, instead of mass, we have moment of inertia of rotating object multiplied by the alpha is angular acceleration. So both are this one. That's what the two formulas are. So mass element, correct? It has a mass if a linear force or angular force torque is given or linear force is given. If the amount of the force or torque given is able to overcome the mass or the I, correct? I is called moment of inertia, or sometimes they put J also, correct? This is called moment, M is called as a moment. Yes, moment, or sometimes they call inertia. Linear force which opposes the motion. I have, as I told you, I have a mass element, I am applying a force and it is sitting on table. You wanted to move, displace some distance. That means there's a force acting which opposes. I am not talking frictional force. The mass itself opposes change of his current position to new position, even when I apply the force. That force only we called as a inertia. That is directly proportional to the mass of the object. Okay. Similarly, with the rotation force opposite called moment of inertia, again that is also proportional to I. I is proportional to mass of the object. Okay. So rotational opposition also happens. Now, where the mass elements are used, they are used wherever you wanted to create a opposition force or you want to store energy. The mass element can store energy. Which energy? Kinetic energy. Mass element can store kinetic energy. We will see later how it stores the energy. The example is flywheel. Flywheel is used in automobiles to store the rotational torque generated by the piston type engine during the power stroke. Correct? You have post stroke, suction stroke, compression stroke, power stroke, and exhaust stroke. Engine developed torque only during the power stroke. Remaining three stroke, it takes power. The piston movement is done by the flywheel. Flywheel stores the energy which it gets during the power stroke. That energy is again used for the compression and piston moving up and down, all those things. So the mass element one uses for storing the energy and use it later. Example, flywheel. Okay. Now, when we talk about the mass element, already I told we will talk about what you call inertia, linear motion, and moment of inertia in case of rotary motion of the object. Correct? When you up, if it happens, this is for rotary motion. If the object is moving under rotary motion, this is under linear motion or straight line motion. Okay. So, what is inertia? Very simple. Tendency of the body, tendency of object or body which we are talking to remain in rest. For example, already object is on a table. This is my table on which object is the mass element having this one, and it doesn't want to move. That is the tendency. That is called as inertia. Because it has a mass, the mass opposes any motion. It doesn't want to move. That opposition with this one is called as inertia. Okay, that is called as inertia when the object in the rest position as a static condition. Static or rest condition. If you try to apply a force to move the object, this object opposes the motion, forward motion. That is called as inertia. Again, as I told you, rotational for opposition rotation motion is called moment of inertia with respect to the axis. As I told, I have a cylindrical disc and it is an attached shaft. When I try to move it, correct, rotation moment and the mass, because the disc contains a mass that opposes the rotational motion. Oppositional rotation motion called moment of inertia. Already I talked into the moment of inertia. We already looked into that acts about the axis, about this axis at which the motion is happening. This is axis about which the rotation motion is happening. That's what is happening. And the moment of inertia is distributed to entire disk. And that depends upon where the particle, because you know that this is made of individual atoms, correct? Billion, trillions of atoms there. The position of individual molecule atom has its own moment of inertia. Total inertia is different summation. Moment of inertia is proportional to radius from the center axis. For example, if I consider atom in this position, this is the center axis from this is the distance d1. If I consider this one, this is d2. So that means that's why you say summation of individual particle is what called I. I is the summation of moment of inertia of individual.
Sir, your voice is not audible. Ima, are you also facing the same issue?
Yes, gentlemen. Just a minute, I'll call him only.
I think his device must have hung like last time. Maybe we can wait for 2 minutes.
1 minute, 1 minute. Let me check. Sir. Hello. சரி ஓகே சரி சார் சரி சார் சரி சார் நாங்கள் வெயிட் பண்ணுறோம் சார் இன்னொரு 10 சரி சார் சரி சார் சரி சார் ஓகே ஷூர் சார் ஓகே friends, I think there is a power cut at IIT, so it will take another 5 minutes to resume, so please be online. Yes, sir. Yeah, no. Tell me, sir.